Hello everyone. So in this lecture I'm going to start generating function that is used to solve some advanced counting problem. Okay, so let us begin with generating function. So guys, this one is very important. Okay, so we can say that for gate point of view also this topic is very important topic, and this one is, yes, we can say that most of the students face the difficulty in this particular topic. So try to concentrate carefully, isn't it? Everything will be clear to you guys, so try to concentrate here. So we'll see what is generating function. So in this lecture, I will define the generating function and we'll see some standard generating functions. And in the next lecture, we'll see the properties of generating function. And in the next lecture, we'll see some problems or advanced counting problems which can be solved with the help of generating function. It will take around 3 lectures, then we can say that generating function will be complete. Okay, so write down the definition or what is the, yes, generating function. So write down. We can say that a generating function is used to solve, we can say that, some advanced counting problem. Advanced counting problems, isn't it? Okay. So yes, let us consider what is generating function. Let us consider, let's say a sequence is given to you. Let's say this is the sequence a0, a1, a2, let's say up to ar. Then this sequence is represented with like that, where r is 0 to infinity, no problem at all. R could be 0 to infinity, no problem at all. Then we can write down, yes, we can write down one power series. We may write a power series like that, yes, of the form we can say that, yes, this sequence is what we can say that a naught, that is multiplied with x bar 0. First term is multiplied with x bar 0, that is the meaning. Second term, whatever it is, that is a1 will be multiplied with x bar 1. Then a2 is multiplied with x square, and we can say that ar is multiplied with x raised to power r. Yes, we can write it like that, g of x. Then g of x is known as what? Generating function, isn't it? I hope this one is clear. So we can say that generating function is written corresponding to a given sequence, isn't it? So whatever be the sequence is given to you, just yes, multiply first term with x bar 0. Yes, remember guys, there is no connection with these zeros. Remember this one, first term, blindly first term will be multiplied with x bar 0. Second one will be the x bar 1, and so on, and sum all these terms, that will, yes, create, or we can say that generate a generating function. And in the closed form we can write it like that, r from 0 to infinity ar x raised to power r, that is the generating function, isn't it? Now we'll see here some standard sequence and corresponding generating functions in open form as well as closed form. So this one is known as, we can say that, open form, and this one we can say that is known as closed form. So remember guys, this one will be helpful to solve some advanced counting problem. So whatever I am going to explain, try to listen everything, isn't it? Because after 1 or 2 lecture, when we'll solve some advanced counting problem, then you will see the applications of generating function. So for the time being, whatever I am going to explain, try to listen carefully, isn't it? Now we'll see some standard sequences and what will be the corresponding generating function. These standard, we can say that sequences and corresponding generating functions will be helpful to you guys to solve some complex problems based on generating function, isn't it? So we'll see some standard. These must be, yes, we can say that clear to everyone. Okay. So we'll construct one table and we'll see some standard sequences and corresponding generating function. Okay. So yes, we will construct one table. So first column header is sequence. Whatever be the standard sequence, some we can say that well-known sequences, and most of the time these sequences or these type of generating functions will be used. That's why we are yes doing these one. And second column header is numeric function. Then we can say that we'll see the generating function in open form, and then finally we'll see generating function in closed form. So just construct one table and we'll see how it came, isn't it? Okay. So yes, these are some standard sequences and corresponding generating function. Okay. So write down first one. Yes, let's say this is the common a naught, a1, a2. Let's say up to infinite this sequence is given to you. And in numeric function we can write it like that or not. AR where R is 0 to infinity. And in open form the generating function will be what? Yes, we can say that yes, in the open form we can say that the generating function will be what? Yes, a naught x bar 0 plus a1 x bar 1. Then we can say that that is a2 x square and so on. And what will be the closed form? We can say that that will be the yes summation r 0 to infinity ar x raised to power r, that is yes we represented with the g of x, isn't it? Okay. I hope this one is clear to everyone. So we can say that this is equivalent to r equals to 0 to infinity ar x raised to power r. So we'll see one by one. Let us consider first one. Let's say one sequence is given to you 1, 1, 1, 1 and so on up to infinity. Then we can say that ar is what? Ar is 1 always. So what will be the open form? We can say that open form will be what? 1 into x raised to power 0 plus 1 into x power 1, then 1 into x square up to infinity. And this can be written like this or not? R 0 to infinity, yes, 1 into AR into x raised to power r, where AR is 1. So what will be the sum of this series? This is, you know, this is infinite GP series, and sum will be the 1 upon 1 minus x. So that is your generating function in closed form, isn't it? Okay. Write down next one, second one. Let's say now the sequence is given to you 1 minus 1, 1 minus 1 and so on, alternating plus minus sign. So what will be the AR? AR will be the minus 1 raised to power r, and this can be written like this or not? Summation r 0 to infinity AR is what? Minus 1 raised to power r into x raised to power r. So yes, we can expand this one. This becomes 1 minus x power 1 plus x square minus x cube up to infinity. Yes, so we can say that this is also infinite GP series with common ratio. Yes, minus x. So it becomes what? 1 upon 1 minus minus x. That is 1 upon 1 plus x. So that will be the closed form, isn't it? I hope this one is clear to everyone. Okay. Next one we can say that third one. Let's say one sequence is given to you 1 a power 1, then a square, then a cube up to infinity. Then we can say that ar is what? A raised to power r. Then summation we can say that r is 0 to infinity. What is ar? Here ar is a raised to power r multiplied with x raised to power r. So this becomes what? We can say that a0 x power 0, a power 1 x power 1, a square x square up to infinity. This is also infinite GP with common ratio equals to ax. So 1 upon 1 minus r, r is ax. So that will be the yes generating function in closed form, isn't it? I hope this one is clear to everyone. Okay, write down next one, fourth one. Let's say what is fourth one. Fourth one we can say that, let's say 1, then minus a raised to power 1, then a square, then minus a cube, and so on. Here we can say that alternating plus minus signs are there. Yeah, so we can say that here AR becomes what? AR is minus 1 raised to power R into a raised to power R. Isn't it? I hope this one is clear to everyone. Okay. Always R starts with 0. Isn't it? R starts with 0. So you can put the value of R and you can see the, yes, corresponding sequence. Now here we can say that here it can be written like that or not. Summation R 0 to infinity, and this is AR is minus 1 raised to power R into a raised to power R, that is multiplied with x raised to power R. So on expansion, this becomes what? A naught a power 0 x power 0 minus a power 1 x power 1 plus a square x square minus a cube x cube, and so on up to infinity. So you can see this is also infinite GP series where common ratio is minus AX. So we can say that 1 minus minus AX. This becomes what? 1 upon 1 plus AX. That will be the closed form. Isn't it? So we see in some standard sequences we see in 4. Yes, the remaining will also be there. Yes, fifth, sixth up to 11 we'll see one by one. I hope this one is clear to everyone. Okay, so I'm going to change. Yes, I'm going to make the change. Yes, we can say that in this same table. So if you return, then I will. Yes, I'm going to erase these one in this topic in this table also, isn't it? So we can say that in this table I am going to erase these one 1 2 3 4. Now we will write next 4 5 2 8, then next 4, and so on. Okay, so I am going to erase 1 2. So fifth one, let's say sequence is given to you 1 0 1 0 1 0 and so on up to infinity. So here we can say that what is AR? AR is 0 when R is odd. Also we can say that it is equals to 1 when we can say that R is even. Yes or no? So here we can say that it becomes summation R0 to infinity. Yes, you only tell me, can I write this like that? That becomes x square raised to power R. Yes or no? So put R equals to 0, then it becomes what we can say that, yes, 1 or not. Yes or no? Isn't it? When we'll put R equals to, yes, you only tell me. Yes, when it is, you only tell me. This is, we can say that, we can write it like that. So put R equals to 0, so it becomes what we can say that 1. And then put R equals to 1, then it becomes, we can say that x square. Then we can say that x power 4, then x plus x power 6, and so on. You can see that, yes, when we'll multiply first term with x power 0, then it is 1. When 0 is multiplied anything, then it becomes 0. Yes, so it is multiplied with, we can say that x power 1, then 1 multiplied with x power 2, then 0 is multiplied with x power 3. So we can say that these odd powers will be eliminated, or we can say that these are multiplied with 0. So we can say that these terms get vanished. Yes or no? Okay. So these we can say that this will be the, yes, generating function. And what will be the, yes, we can say that this is also infinite GP series in which common ratio is x square. So sum will be a upon 1 minus r, that is x square. Isn't it? I hope this one is clear to everyone. Okay. Write down next one, that is sixth one. And sixth one is given to you 1 0 0, then 1 0 0, then 1 0 0, and so on. This sequence is given to you. So what is AR? We can say that AR is, we can say that that is 1, we can say that when R equals to multiple of 3, where n is 0 1 2 3 and so on. Also we can say that AR equals to 0 otherwise. Yes or no? Isn't it? Now, yes, we can write it like that or not. Yes, that can be written like that or not. X cube raised to power R. So here we'll see 1 plus x cube plus x power 6 up to, yes, infinity. Yes or no? So this one is also, we can say that infinite GP with common ratio 1x cube. So it becomes 1 upon 1 minus x cube. That is the closed form, or we can say that that is the generating function. Isn't it? Okay. Write down next one. Yes, next one we can say that that is seventh one, or we can say that that is important also. This is most important. Remember, guys. So here one sequence is given to you, that is n minus 1 C0, n C1, n plus 1 C2, then n plus 2 C3, and so on. Remember here n and r both are incremented by 1. Remember this one, isn't it? Both are incremented by 1, isn't it? Okay, so remember this one. So here, listen me correctly. Yes, R starts with 0 and n starts with n minus 1. Then n minus 1 plus 1 becomes n, 0 plus 1 becomes 1. Then again n plus 1, R plus 1. We can say that in n and R, we can say that both are incremented by 1. So yes, be careful. So here we can say that AR is what? N minus 1 plus RCR, isn't it? Yes, you can put R value 0, then it becomes n minus 1 C0. Then put R equals to 1, then it becomes NC1, and so on. So we can say that that is the numeric function of this sequence. So guys, remember, yes, what will be the generating function? Yes, R equals to 0 to infinity, and this is n minus 1. AR is n minus 1 plus RCR, that is AR, and that will be multiplied with x raised to power R. So if we expand this one, then this becomes n minus 1 C0 x raised to power 0, then NC0, that is x power 1, sorry, NC1, then it is n plus 1 C2 x square, and so on. Or we can say that this is kind of, we can say that some binomial kind of expansion, and by using the properties of binomial expansion, we can see that this is the sum of, we can say that 1 minus x raised to power minus n. So this is what we can say that this is 1 upon 1 minus x raised to power n. Yes or no? So remember this one, we can say that some binomial identities are applied, and this sum will be the, yes, 1 upon 1 minus x raised to power n. And remember guys, this one is important one. Listen me correctly, seventh one I already written here. This one is important one. In the most of the questions or previous year gate questions, everywhere you will see this one, isn't it? Okay. Next one, eighth one, we can say that, let's say a sequence is given to you NC0, NC1, NC2, let's say up to NCN, isn't it? Now here AR is what? NCR. So here R is from 0 to infinity, but once R exceeds, yes, R exceeds N, then if NCR, in NCR R is greater than N, then that becomes 0. So no problem at all. Okay. So we can say that here we can write it like that, R equals to 0 to infinity, and this is NCR, yes or no, into x raised to power R. And you know very well what is the sum of this one. Yes, we can say that sum of this one is 1 plus x raised to power n. Yes, I told you guys in the binomial identities it becomes NC0 x power 0 plus NC1 x power 1, then NC2 x square, and so on. And we can say that sum of this one is 1 plus x raised to power n. Yes or no? I already told you yes about this in binomial identities and binomial expansion. Okay. Okay, so we can say that these are seventh and eighth one. We'll see remaining one also. So I'm going to erase these ones also. Next one we can say that that is, let's say, ninth one. So ninth one sequence is given to you 1 by 0 factorial, 1 by 1 factorial, 1 by 2 factorial, 1 by 3 factorial, and so on up to infinity. So you remember, yes, you know very well, this is AR. AR is what? 1 upon R factorial. R is from 0 to infinity. So this becomes what? We can say that this becomes Yeah, summation we can say that r from 0 to infinity x raised to power r divided by r factorial. It is we can say that 1 plus x raised to power 1 divided by 1 factorial, x square divided by 2 factorial. Then we can say that x cube divided by, yes, we can say that 3 factorial and so on. And what is this series? We can say that this is, yes, a series corresponding to e raised to power x. Yes or no? Might you remember this one? Yes or no? Okay. So that is ninth one. Write down next one. Yes, 10th and 11th. Yes, write down 10th one. Yes, we can say that, let's say this is 10th one. Remember this one. Yes. Let's say uh, 0, 1, 2, 3, 4 and so on. This is the given sequence. Now what is AR? You only tell me. We can say that AR is R only. So this becomes what? Summation R 0 to infinity. Then this is R into x raised to power R. Yes or no? So this becomes what? X plus 2x square plus, we can say that 3x cube plus 4x power 4 up to infinity. And you know very well this becomes what? This is AGP series or not? Yes, and I already told you, yes, during the summation, yes, in the previous lecture, how to solve AGP series. I already told you guys that. So this is AGP series, and after solution you will see, yes, the simplified expression will be what? X upon 1 minus x raised to power 2, isn't it? Okay, I hope this one is clear to everyone. Okay, so yes, I'm going to proceed next one, that is 11th one, that is also important. Okay, yes, 11th one. Yes, last one, 11th one. Let's say sequence is given to you 0, 1, 4, 9, 16 and so on. Then what is AR? AR is R square. So it becomes what? R is 0 to infinity. We can say that it becomes R square into x raised to power R. So what will be the series? Yes, we can say that 1 square x power 1, 2 square x square. Then we can say that 3 square x cube and so on. Yes, remember this is not a, yes, we can say that this is not a AGP series. Here GP series is there but no AP series. 1 square, 2 square, 3 square, this is neither AP nor GP. Remember this one. So this is not an AGP series. So what we'll do? Yes, we can say that this is not an AGP series. So we cannot apply AGP. Yes, we can say that AGP method, how to solve AGP. But remember in this particular series, yes, if we apply the formula of or method of AGP two times, then we will get the solution. Isn't it? Okay. So just try it. One simple one is there. Let's say s equals to, we can say that 1 square x power 1, then 2 square x square plus 3 square x cube. Yes, up to infinity. Let us consider this is equation 1. So whatever be the GP series, the common ratio in that GP series is x. So multiply the whole equation by x, xs. Now multiply first term and write it below to the second term. That is the procedure. So it becomes 1 square x square. Then multiply second term with x and write it below to the third term. So it becomes 2 square x power 4, x power 3 and so on. Isn't it? Yeah. Yes, we can say that, let's say this was 4 square x power 4. So it becomes 3 square x power 4 and so on. Now subtract these one. Yes, after subtracting this becomes what? We can say that s into 1 minus x. Now it will be, yes, we can say that x power 1 plus 3x square. Then we can say that 5x cube. Then we can say that this is 7x power 4. Yes or no? Isn't it? I hope this one is clear to everyone. Okay. So this is up to infinite. Yes, now you only tell me, now this equation becomes what? AGP series. Yes or no? This becomes AGP series. Now apply, yes, this method again one more time. Isn't it? Now in this AGP again GP series is x, so multiply this with x, so it becomes s into 1 minus x into x. Yes or no? Isn't it? Now multiply this one with x, so it becomes x square, and write it to the below to the second term. Yes, this is, yes, multiply second term with x and write it below to the third one. So this becomes 3x cube, then this is 5x power 4 and so on. Now subtract these ones, so it becomes x power 1 plus 2x square. Then we can say that plus this is also 2, all are 2 only, plus 2x power 4 and so on up to infinity. Now you can see, yes, this becomes what? We can write it like that or not? Yes, we can say that this can be written like that. Yes, x plus take 2 as a common, so it becomes, yes, we can say that x square plus, yes, we can say that x cube plus x power 4 up to infinity. Yes or no? So this is infinite GP. So sum is first term divided by 1 minus common ratio, that is x. So after solution it becomes what? You only tell me. Yes, we can say that this is after simplification x square plus x divided by 1 minus x. And this is equal to s into 1 minus x into x. Yes or no? So s will be, yes, we can say that x square plus x. Yes or no? And we can say that divided by, yes, we can say that this one, remember this one, left hand side after simplification becomes what? Remember this one? Yes, left hand side after subtraction it becomes s into 1 minus whole square. Yes or no? Isn't it left hand side? So this is equal to, we can say that s into 1 minus x whole square. So ultimately, yes, we can say that here s value will be what? X square, or we can say that x into, yes, x into x plus 1 divided by 1 minus x whole cube. So we can say that that is the sum. So in this type of, we can say that series, we can apply the AGP solution method first time, then we will get AGP. And if we get AGP, then again apply the same formula or same method to solve the AGP. Yes or no? Then again we will get the, yes, finally we will get one GP series, and easily we can write down the solution. Okay. So we can say that here, yes, what will be the, yes, we can say that here we can write down what will be the generating function. Yes, we can say that generating function here will be what? That is x into, yes, x plus 1 divided by 1 minus x whole cube. Isn't it? We can say that these can be asked as a questions also. Okay, but these are some standard one, no need to remember anything. Yes, just I said you, yes, one important is there, what is e raised to power x expansion. These one we can say that you can remember, otherwise you can derive, yes, at the moment only. Yes or no? You know the procedure, what is the sequence, what is the generating function corresponding to that particular sequence. One thing is only there, what is, yes, multiply first term with the x bar 0, second with x bar 1 and so on. Whatever be the series, summation of this series, yes sir, try to solve or simplify that particular series, that will be the generating function in closed form. And in open form it will be the directly whatever present, means after multiplication each term with the x bar 0, x bar 1 and so on, that is only the open form, that is open form generating function. And after simplification of that series, whatever you got, that will be the closed form of that particular generating function. I hope this one is clear to everyone. So in the next lecture, we'll see the properties of generating functions, how the questions has been asked on this particular topic, and this one is very very important topic in entire combinatorics. And we can say that, and finally, yes, after 1 2 lectures, we'll see how to generating function is used to solve some advanced counting problems, isn't it? Yes, if you remember in some previous lectures, some problems are left out, and I said at that time that these problems can be solved with the help of generating functions. Yes or no? So those problems also will see the Yes, how to solve with the help of generating function, where we can say that where upper constraints were there, more than one upper constraints, yes or no, or any number of constraints are there, then we can solve those type of questions with the generating function. Now, how we can solve this will see in the next coming lectures. Okay, I hope this one is clear to everyone. Okay, thank you so much.